Okay, let's talk about, we're going to talk about tangent lines a little bit. That's going to be a pretty important topic for us along the way throughout the semester here. So, looking at tangent lines and secant lines today anyway. When does anybody have an idea of what I mean by secant line? Tangent line you may be a little more familiar with. You have the tangent. Well, you have secant and tangent and trig, but what we're referring to here is probably the most often before calculus time you would see a tangent. Secant line is with a circle. I mean, it applies really. We can apply it to function, any function as well. But when I talk about a tangent line, the tangent line is a line that just comes in and just touches one point of the circle. That's a tangent line. And then secant. Do I have an idea there? Secant line. A secant line, it goes across and hits it at 2 points. And it doesn't have to be necessarily through the middle either. It's just any line that goes through there and touches it at 2 points. That's a what we call a secant line. Now, what we're going to deal with, of course, is not circles, but it's more function type graphs. But the idea is the same. Tangent line is where it just kind of comes in and touches it at one point there, and then a secant line, it touches it in two. And the idea is that we're talking more close by. So if I've got a function here, and I want the secant, a tangent line at that point, the tangent line comes in and just kind of touches it. Excuse my missing there. Okay, that would be a tangent at that point, and then a secant at that point would touch the graph in two places. Whoops, I didn't do a good job there, so let me go back this way. Make it easier on myself. Okay, that would be a secant line. Okay, tangent and secant. Same idea. All right? Okay. Well, with that in mind then, let's take a look at the tangent line of a function, kind of what we're alluding to here. But I've got the handout there to you. And so let's this is the tangent line of a function handout. So number one, we've got the graph of f of x equals x squared plus 2. Try to move over here a little bit. Okay. So we've got f of x equals x squared plus 2. So draw the tangent line of the function at the point 1, 3. So A, we're just going to draw on the graph I have there provided. Draw the tangent line of the function at the point 1, 3. So over here at 1, do a little better job here. So at 1, 3, call it right there. I'm just wanting you to freehand in a tangent line there. Okay, do your best tangent line you can. That's the best one I got. Okay. So the tangent line should just kind of touch it. It's going to be hard just to make it look like it's just one point because it's not real steep or it's pretty steep there. But, okay. So that's our tangent. We'll call that our tangent line. So B part of number 1, how could we figure out the slope of that tangent line at the point 1, 3? How could I do the slope of that tangent? Well, it's a line, and so there's a couple of options there to figure out. You know, I'm just talking about of the one we did. We'll figure out a way to actually compute it exactly in our coming talks here. But we're just trying to figure out from that line what that slope would be. Okay, so I've got we have a slope formula, difference of the y's or difference of the x's. And, you know, if you want to, you could do that because, like I said, we've got 1, 3 here, and then you could pick out, well, it looks like it's at this such an other point, get that other point. What I'd like for us to do, though, is to think of, instead of that slope formula, think of the slope in terms of another kind of phrase we use. Have you ever heard the slope called the rise over the run? Rise over the run. So that's the way I'm going to do it here on this one, and we're going to do it another way on number 2. So anyway, slope is rise over run. So we'll use that definition, if you will, of slope a few times along the way. Rise over run. So yeah, it's the same idea, I guess, as the slope formula, but just pick out, well, how far. If I go from this point, let's just say I picked out that point. If I go to that point, what's the rise and what's the run? The run, of course, is let me get rid of that 1, 3. This would be the run, and this would be the rise. So yeah, you're just going from a point to a point. Just figure out run. And what I usually do is I usually, if I can, do my run as 1, and that makes it a little bit easier to calculate. The run is 1. And so then figure out what the corresponding rise is. Maybe I went a little too far out. 1, maybe right there. Okay, so if I run 1, what does my rise come out to be to get to that tangent point, tangent line there? I don't know. This is an approximation, so yours may be slightly a bit off from mine, but for mine, it looks like that rise is 2 if I run 1. And yours may be, hey, it's a run of 1.5 and a rise of 3.1. It's, you know, it's subjective a little bit here, what way we're doing it this way, okay? Because I may have not drawn that tangent line just right. I think I did actually a pretty good job on it here on this paper, but okay, with me there? How I got that? Because it may ask you to do that from time to time, estimate that slope by using either, like I said, rise over run, or you can use the slope formula as well. But okay, so I'm saying that's a 2. Well, I've already mentioned the problem with doing it that way is that's very subjective. That may be, actually that's pretty good, I did a pretty good job there, but all I know about that is that's an approximation of that slope, because that tangent line I drew in, it may be a little steep, it may be not steep enough, you see what I'm saying? So this is just an approximation. And so is there a way to figure out what the exact value of that tangent slope is? Okay, and so that's what we're going to work on in the next few minutes here. But that's a pretty good approximation. I mean, yours may be 2.5, maybe 3. That's okay. All right, it's just an approximation. One thing, the one thing we should be able to tell by drawing in like this is that the tangent line definitely has a positive slope, right? Because it's uphill from left to right. So, and that a lot of times that's really what we're looking at. Is it a positive or is it a negative tangent slope? And then we can figure out what the other stuff is, if we need it more precisely. But if it was over here, the tangent line would be a negative slope, okay? And then there's some other things. Getting a little ahead of myself, but anyway, it is definitely a positive. So if you're in the positive range, you're good on that one, all right? Number 2. So let's, number 2, let's estimate this secant line, the tangent line slope by using a secant line. So we're going to estimate the tangent line, but we're going to use the secant line. Here's why. Okay, so I've got my function here. And I'm not going to subjectively draw in a tangent line. I'm going to do it with a secant line, because the deal about the secant line not only has this point on the graph, but we've got that second point on the graph. And so there's no subjectivity to it, because I'm going to another point on the graph. I know what that point is. You know, I'm going to figure out, you know, how far I want to go. Let's do it with the secant line, with the second point having x value 2. Now, so I start here at 1, 3, and so I'm going to go to a secant line from 1, 3. I'm going to go out to that second point at 2. All right, and so again, that's where, you know, I'm not doing any kind of it's not subject to my drawing here, because I know my function is x squared plus 2, right? And so if I go out to the x value 2, then I'm locked into what the y value is, aren't I? Be 6. 2 squared plus 2, that's 6. Okay? All right, so yeah, so now that's where I'm going to, so this is going to be the slope of my secant line. Slope of that secant line, so I'm taking this right here. I'm getting the slope of that line, which is not going to be the tangent line slope, but it's a fairly good estimate of it, because it's, you know, it's positive slope, its steepness is close to it, close to the tangent line slope, so it's a pretty good estimate, but we'll do better, but this is a good start. All right, so yeah, that's where our slope formula, difference of the y's over difference of the x's, y2 minus y1 over x2 minus x1. We are going to use that formula here. Second y is all that means, so it'd be 6 minus the first y is 3. Second x is 2 minus first x is 1. So that gives me 3 over 1, which is 3. Now that's the slope of that secant line there. Okay? That's maybe not a better estimate than the first one, but like I said, it's, you know, those two values, you know where those came from. It's not based on something you drew in there, so that's, I guess, what's better about that one. Now, how could we use a secant line and do better than that estimate, you think? Well, if we come here and do on number 3, a better estimate, oh yeah, by the way too, what we're going to do is call our, this is the way the book does it, they'll call this first point P and this second point Q. And so that's the estimate of the tangent line slope using the secant line through P13 and Q26. All right, so let's get a better estimate, and let's use Q as 1.5, comma, you know, whatever 1.5 goes with, okay? So what did I do there? Well, I pulled my Q point in closer in, didn't I? All right, so instead of, yeah, I've got the graph there. So I've got 1.3 for P. And then my Q, I'm not going to go all the way out to 2, I'm just going to go out to 1.5. You see, I pulled it in a little bit, and so now I'm getting closer to that tangent line, aren't I? I've stepped back, come in closer than 2.6. So now I'm at the point 1.5, and what's the other point that goes with it? Well, it'd be 1.5 squared plus 2 would be my y value there. 4.25, is that what it would be? Is that right? Checking on that. 1.5 squared plus 2 is 4.25, I believe. Okay. Yeah, 4.25. All right. So the slope of that secant line then, and we'll call it, slope is m, so we'll call this one the MPQ. So the slope of that secant line, that using that P and that Q, 1.3 is P and Q is 1.5, 4.25. What do I get there? Well, again, difference of y, so it'll be 4.25 minus 3, and then 1.5 minus 1. So it's 1.25 divided by 0.5. And so that slope is, was that 2.5? Okay, so here's sort of a hint as to what we're going to do with this. All right, so if I put these two results in a table here, and the table, what the x value I'm looking at on my table is the x value of the q. So that's what I was changing. I changed the x value of the q from 2 to 1.5. Okay, you with me there? And then over here, what I got was the slope of MPQ then, the slope of that secant line. So it was 3 here, and then 2.5 here. Okay? Okay, so you kind of see what we're doing here. We're kind of doing our limit thing, aren't we? We're getting our x values. So I'm trying to find the slope at 1. And so I'm getting these x values closer and closer into 1, right? The xq values. So where might I go here next? Well, I could go to 1.25, or let's jump to 1.1. So that would be even closer to the 1. All right, so I'm not going to draw it. Let's just compute it here. So the fourth one we'll do here. What's my MPQ? All right, so now I'm going to use the Q point where x is 1.1. So what's the MPQ there? Well, I've got my x value, so the difference of the x values, again, what I'm looking at is P is 1.3, and then Q is the 1.1, comma, whatever y value goes with that. So it's the same every time. So now I just have to figure out what is the y value that goes with that. Well, it's always the same function. F of x equals x squared plus 2, and so that would be 1.1 squared plus 2. Let's see, 1.1 is 1.21. No. What is 1.1 squared? Is it 0.121?
It's 1.21.
1.2, okay, thank you. So it's 1.21 plus 2, so that'd be 3.21. Yeah, I was right. Okay. I was doubting myself there. Okay, so the MPQ then would be 3.21 minus 3 divided by 1.1 minus 1. So we get there 2.21 divided by 0.1, so we get 0.21, sorry. 0.21 divided by 0.1, that's 2.1. Okay, I think that's as far as I'm going to go on this one. I may go a little farther in the next one, but hopefully you kind of see what we're trying to do here. We're trying to get these secant lines, which, you know, we can compute those. Those aren't subjective. We know the function, so we can compute the x and off the x value, we can compute the y value. So, you know, there's no getting around that. But setting up this way, we can kind of see, well then, since I'm getting my x cubed closer and closer to 1, these, hopefully you see, these secant lines should be tending towards that tangent line. And so, yeah, so you can see here that these are definitely maybe going somewhere, but if you flip on the other side there, you can kind of see what we're doing, hopefully. What we've got there on the back side of the handout is I've graphed the secant lines in number 1, 2, and then my third one I didn't draw, but it's drawn here on the, so here's our graph, and then we've got secant line 1 kind of comes in like this at 1, 3, and then secant line 2 comes in like that, and then secant line 3 comes in like that. And then the true tangent line, I kind of jumped ahead, but the true tangent line, well, it's really, really close to what you got there for number 3. That's the true tangent line. So you can see as we step towards the, you know, those were based on xq was 2, xq was 1.5, xq was 1.1. That's where those 3 coming from. But you can see, yeah, those secant lines are tending towards being closer and closer to that tangent line. So secant line 3 is really pretty close to, and it's even a little closer than I've got it drawn there. You see it on the handout better, but that secant line 3 is pretty close to the slope of that tangent line, isn't it? Okay, all right. Now, in the next step here, we're going to then, well, all right, so based on this idea, you know, setting up this table, then I can kind of do the limit thing I was doing in the previous section. Yeah, I'm looking at a limit as these x values. So these x values were going towards 1, weren't they? What is happening for my m? Well, it looks like the m, meaning the slope of the tangent line, what does it look like the m's are going to here? Well, it looks like, and we might need one more there, maybe do 1.01, and that would maybe clear it up even more, but it does look like those are tending towards 2, doesn't it? And that sure enough is that's going to be the slope of our tangent line there. That's where we're going with this. Okay? All right. Any questions or concerns about that? Okay. All right, so let's do this one. All right, let's, yeah, so let's continue that one on. And like I said, it looked like it was going towards 2, but a few other things. All right, so let's do the same function, f of x equals x squared plus 2. All right, let's, again, what we're going to do here is use a table to approximate, to find, let's say, find the slope of the tangent line at 1, 3. Because this is, that hopefully gives you an idea of what we're doing here, and this kind of shows you what you'll kind of need to put down for me here. Okay, use a table to find the slope of the tangent line at 1, 3. Okay, so we already established here what I want to do is I want to look at those XQ values, and I already did 2 and 1.5 and 1.1, but there's probably, to be certain, using a table anyway, we probably need to look at some more things, okay? So again, the difference on this table compared to the previous tables that we did with limits is I'm not doing function values here, I'm doing slope values, where, you know, MPQ, so this is the P point, and then Q, all right, so let's think about Q here. In general, then, what's going to be my Q values? Like I said, those are going to be my X values. So let's just call the X value of the Q X, okay, because it's going to be a variable sort of thing. What then are my Y values for that Q point? Well, it's whatever I plug in X, whatever I get out of this function, right? So isn't the Y value going to be X squared plus 2? It's going to be X squared plus 2. So that just gives me kind of a general way of thinking about the Q point there. All right. Now, let's go ahead and take this another step here. All right. So if that's my P and that's my Q, what's my MPQ then? What's the slope of that? And again, this is going to be, so this Q gives me that secant point to get my secant line. What's going to be the slope of that secant line? Well, based on that general Q point there, it's the same thing, right? Difference of the Y's or difference of the X's? Difference of the Y's, so I take Y2, X squared plus 2, minus Y1, first Y, 3. And then divide that by the difference of the X's, so it'd be X minus 1. Okay? So that's X squared, if I simplify, X squared minus 1 over X minus 1. Now, the reason I do that is because now we can let's use our calculators to compute these. I mean, we can do these by hand because we're going to get, like I said, I'm going to do some even, with even more decimal places here, 1.01. And so I'm not going to plug in the function for these problems. I'm going to plug in the slope equation. All right, you with me there? Into the calculator for my y equals, y1 equals. So I can kind of use the same procedure as before. It's just, so let's go and put that in for our y1 value. Put in this for the y value. So it'd be parentheses x squared minus 1. Close parentheses, forget that, divide that by parentheses x minus 1. Yeah, and so let the calculator do the work for us. I mean, we can do them by hand if you want, but, and we'll go ahead and check 2. Yeah, 2, we get 3, we knew that. 1.5, we should get, what do we get? 2.5, yeah. And that was 2.1, wasn't it? Just checking. Yeah, it's 2.1. But since we've got it set up, you don't have to do much more work to do 1.01. So we get closer to 1 there, 2.01. And then even more precisely, go to 1.01, right? So I think we can see the trend. Again, that trend is those slopes look like they're going to 2. Now, one other thing that we talked about on limits, this is, we'll actually call it a limit, that's a couple of days down the road, but remember on limits though, we've only looked at one side of this, haven't we? This is as the x gets closer and closer to 1, but it's from the right, right? What else do we need to look at? From the left, right? Correct. From the left, correct. Yeah, so we've got to look at it from the left as well, if we're going to use a table to figure these things out. And so, kind of extend our table here. If I looked at, so these are x values approaching 1, but they're from the, the right, yeah, 1 from the right. Let's do our table over here, x approaching 1, but from the left. You see what I'm saying? So what would that be? If I approach 1 from the left, so less than 1, 0.9, 0.99 for x, q. You with me there? Those values, those would be the x values to look at on the other side of 1. Getting closer and closer to 1, but from the other side. But again, since we already know the MPQ is x squared minus 1 over x minus 1, those wouldn't be that hard to plug in, but let the calculator do the work, and that's even easier. Yeah, looks like we're in good shape. 1.9, 1.99, 1.999. So those also appear to be going to 2. So what that's telling me is that these two being 2, that's telling me that slope of that tangent line looks like it's going to be 2, because as we get closer and closer to x equals 1, the slopes are going to 2. And so that's going to be the slope of my slope of the tangent line, is what these values are going to. Slope of the tangent line is going to be m equals 2. Okay? Make sense? Sort of? Hopefully. Okay. Let's look at it. All right, let's use a table to approximate the slope of the tangent for f of x equals 4x minus 1/2 x cubed at the point 2,4. Use a table to approximate the slope of the tangent for f of x equals 4x minus 1/2 x cubed at the point 2,4. Okay, so on our table, what we want is we want x of the cube, because this is our p point, right? And so the x value in our table is the x value of the q. So q is going to be x comma whatever the f of x is, which in this case, the f of x is 4x minus 1/2 x cubed. So that's going to be our y value for the cube. So on the table, what I want